Hello and welcome. Today we're going to be demonstrating or deriving the phase-amplitude decomposition for trig expressions. So the idea here is the following. If we have A times cosine theta plus B times sine theta, we can re-express this as C times cosine of theta minus phi. The idea here, if we're given this, if we're given that, the idea here is that this is a simpler expression where C is going to be equal to this amplitude, and then phi is what we call the phase shift. And what we're going to find out is that C is equal to the square root of a squared plus b squared, and that tangent inverse of phi is equal to b over a. All right. So to get an understanding of how to derive this, what we're going to do is start with really important, the angle difference formula. So the angle difference formula says the following. If you have cosine of A times cosine of B plus sine of A, sine of B, where A and B are two angles, this can be re-expressed as cosine of A minus B. And we can see up here, that looks a lot like our expression there. And this expression here looks a lot like our expression there. So to get an understanding of how this works, let's see if we can start again from A times cosine theta plus B times sine theta. All right, so what I'm going to do here is I'm going to multiply this whole formula. So in this case, A and B can be any value, any set of values. In order to best capture this, what we want to do is actually we're going to multiply the equation, this formula, by a squared plus b squared, all square rooted. And we're going to divide it by the same quantity, so we haven't changed the expression at all. So the numerator, a squared plus b squared, square rooted, I'm going to leave outside. And then we're going to have a over a squared plus b squared, square rooted, times cosine theta, plus b over square root of a squared plus b squared, times sine theta. All right. The next thing to note here is that that a over the square root of a squared plus b squared, if I square it, and I do the same thing to the other term and add these two together, then I get a squared plus b squared all over, a squared plus b squared, which is equal to 1. So this is the Pythagorean identity. And note also that a over square root of a squared plus b squared, and that b over the square root of a squared plus b squared. They're in the interval -1 to 1 by definition of how they're structured, right? So what that means then, of course, is that this looks a lot like this could be a cosine of some angle. Again, we don't know what phi is, but it could be the cosine of some angle, and that can be the sine of the same angle, because we know if I square these two and add them together, I get 1, just like above. Okay. With that said, then, what I can do is, and now I'm going to move to a new page here, and start over again, and then we have the following, which is we have a over root a squared plus b squared. I'm just going to rewrite what we wrote before. Like this. And now we can rewrite this as cosine of phi. Oh, we have to remember that on the outside we have that other square root of a squared plus b squared. So I have here the square root of a squared plus b squared again. And I can rewrite that now as cosine theta plus cosine phi plus, sine theta times sine phi. Right, and here we can use the angle difference identity to get square root of a squared plus b squared is equal to cosine of theta minus phi. All right. And then, of course, we can let or define our constant c to be equal to a squared plus b squared square rooted. And we can get the following. I'll just write it up here. There's my c times cosine of theta minus phi. Okay, so there we go. The only other thing we have to note then is, okay, how do we find phi? Well, we're going to do that by, remember that sine of phi was equal to b over square root of a squared plus b squared. And if we divide that by cosine of phi, which is also equal to a over the root of a squared plus b squared, that becomes the tangent of phi, which is equal to b over a. And that's because, of course, we have a common factor of 1 over a squared, square root of a squared plus b squared, which cancel out and just leads you with the two things we had before. All right. So one might be tempted, of course, to, what I'll just say about this is, how do we find phi? What is it equal to? Well, we can take the inverse of tangent of b over a, but I'm going to put provided a is positive, in which case the phi value will be within negative pi all the way to pi. Oh, sorry, negative pi over 2 all the way to pi over 2. If a is negative, what you're going to have to do is add, you're going to have to shift things by 180 degrees or pi radians to find that out. Okay, so that's the derivation of how we get between the sum of trigonometrics to the amplitude phase thing. What I want to show you now is just an example with real numbers. So let's consider the following problem. So if I have 2 times cosine of theta plus the square root of 12 times sine theta, what I want to know is what's the amplitude and the phase shift that best describes this function. Well, I can compute it straight away. It's going to be the square root of 4 plus, that's 2 squared, plus I'm going to square the square root and get a 12. That's the square root of 16, which is going to be 4. All right. And then finally, tangent phi, which is going to equal square root of 12 over 2. That's the same thing as 12 is the same thing as 3 times 4 over 2. So I get a square root of 3. And then I pull the 2 out, and that gets me a 2. And then I get a square root of 3 sitting there. Now let's understand what this is. The square root of 3, that's the same thing as, of course, sine phi over cosine of phi. And we know that if phi is equal to pi over 6, then we have right here that that's going to be let's write it this way, that we have the square root of 3 there. So we know that that's going to be the same thing as square root of 3 over 2 over 1/2, like that. So that's going to be the same thing as sine of pi over 3. And that's going to be the same thing as cosine of pi over 3. Okay. And so, of course, our phi is equal to pi over 3. All right, so putting it all together, 2 times cosine of theta plus root 12 sine of theta can be expressed as 4 cosine of theta minus pi over 3. Okay, I hope that clarifies how to find the phase amplitude decomposition of a sum of trigonometrics. Thank you very much.